Okay, we're going to have a quick look at Hooke's law, which we looked at very briefly at the end of term, but because it was a bit of a rush, some of you weren't here and so on. Good news is there's not a huge amount to know in year 9. The first thing to know is that Hooke's law is all about materials, and it's often related to springs. A typical spring, you've seen springs, and we played around with them one lesson. If you attach that spring to a clamp, so it's clamped like that, and you add weights to it, there's a certain pattern as to how it extends. So what do we mean by extend, first of all? Well, we have the original length of the spring. That's if there's no force on it. So if you just hold a spring, how long is it? Let's say it might be 10 centimeters. We then add on some weight. Let's add on a 1 Newton weight. Okay, remember that's not a mass, that's a weight. Weight is measured in newtons. Mass is measured in kilograms. When we add on that weight, it might extend to, say, 11 centimeters. Well, the extension would be 11 minus 10, so that would be 1 centimeter. So we know that if we draw up a table of force and extension, we know that no force creates no extension. I mean, if you look at something, if you don't put any force on it, it's not going to get any longer. We know that 1 Newton created 1 centimeter extension. If we then add on another weight, so we now have 2 newtons. Well, this time the spring is going to extend a bit further. And to work out the new length, we get a ruler, put it beside this. Remember, making sure that we put it right angles to the ground, and we don't get the parallax there. Remember, we avoid that by measuring at eye level. So measuring at eye level. You can see that this is now extended, in this example, let's say to 12 centimeters. So now to work out the extension, we do the 12 minus the original length of 10, and that gives us an extension of 2 centimeters. So we know, if we keep filling in our table, that 2 newtons created 2 centimeters of extension. Or you can measure it in meters, either one's good. Well, what's this all going to look like on a graph? Well, if you plot the force, and this is the graph you need to know, against the extension, like this, well, what does it look like? Well, if you plot your points, you're going to find that you get a nice straight line like that, especially at the start. What is happening here? Well, this straight line suggests there's some sort of relationship, and physicists love straight lines because it suggests one thing is related to another. In this case, force is related to extension. And unfortunately for you guys, you will be to this by Hooke, who discovered this relationship. And this is why it's called Hooke's law. It's because the force and extension are directly related. We say they're proportional. If you double one, the other doubles. And what does this look like on a graph? Well, you're looking for a straight line through the origin. That's the origin there. So 0, 0. So a straight line through the origin tells you that it's obeying Hooke's law. So if I doubled the force, if I now went from 2 to 4 newtons, well, you can probably spot the pattern. This is going to double, so we'd get 4 centimeters extension. And this goes on like this, but eventually you reach something called the elastic limit, and it no longer obeys Hooke's law, and that's when it starts to curve. So when it starts to curve, this is not obeying Hooke's law, so not Hooke's law. But really the key thing you need to know at this level is, for Hooke's law, it's a straight line through the origin. Okay, we're going to have a look at the very last part of Notes Quest, which is light. And remember, you did this little experiment where you got those cute little mirrors out with a protractor, and you found the law of reflection. So let's have a look at reflection first of all. Well, this is a mirror here. This is the shiny part. This is the back. It's normally represented by dashed lines. Let's put a ray of light. Let's do the light ray in red coming in like that. Now, the first thing you always do when you've got a ray of light hitting a material is you draw something called the normal. And you need to remember that. It's an imaginary line. It doesn't exist, but you just draw it to help you measure angles. That's called the normal. This ray coming in is called the incident ray. Seems weird, but you need to just learn that. It's called the incident ray. This angle here, we call it I. This is called the angle, and you probably guessed it, given it's the incident ray, this is called the angle of incidence. Remember, it's always measured from the normal. Common exam mistakes is to measure it from the mirror to the ray coming in. This is not right. It's this one here, over here. In fact, that's so wrong, I'm going to rub it out. There we are. Good. Right, well, what happens? Well, as you remember from the experiment, this then reflects off the mirror, and you found that this angle here, which we call the angle of reflection, makes sense. It's the angle between normal, remember this imaginary dotted line down here, and the reflected ray, which is that one. Don't forget to draw arrows on your ray so you know which way they're going. Look at those two lovely arrows there. And we found that these two angles are equal. The angle of incidence, which we represent with I, equals the angle of reflection. This is called the law of reflection. And you can use a protractor in your exam to measure angles and check they're the same. Remember, these two are always equal. Let's have a look at now drawing a reflection in a mirror to see what it shows us. So I'm going to clear that away. I'm going to draw a nice mirror, this time on its side. Remember, this is the shiny surface here. This back bit with the dashes is the back of the mirror. I'm going to put a little object over here, a red dot. We're going to look at the mirror from down here. Now remember, the way to find where the image appears is this thing. Right, remember when you look in a mirror, you always appear the same size and the same distance behind the mirror. So what you can do is get a ruler. Oh, hello, there's a nice little ruler. Didn't know I had that. Line it up with your image and make sure it's right angles to the mirror. So you can see that's right angles there. And if we draw across, whoop, and move it up now to the top, again, make sure it's right angles. It's a bit easier on paper, a bit over the shop, that will do. That won't do, it's not quite there, but anyway, let's go with that. And if we measure this distance here, let's get rid of that now, see you later. If we measure this distance here, and remember it's the same distance behind, we can actually draw where the image is going to appear. Once you've done that, we need to now draw some rays to show that that's where the image will be. What you do here is you draw a ray, just take the top of the image, draw a ray going down. Oh, that's awful. Needs to be a nice straight line. So actually, what you should do is get your ruler. There it is again. And you can do a ray going anywhere on the mirror. Let's just go to there. So nice ray going down, hitting the mirror there. Remember, what you can then do, like we just learned, is you can draw the normal. Remember, it's the imaginary line where the ray hits the mirror. You can measure this angle with a protractor and then draw it the same angle down there. And that will be your reflected ray. So I've not got a protractor here, but you will use a protractor in the exam. Have a look at that. What do you think is missing? Well, hopefully you spotted it. I've not put any arrows on my rays. Now, this doesn't show you where the image actually is. So what you have to do now is dot back to show where the image is. Now, you can see that earlier I drew it very roughly and it's wrong because these dots should meet the top of the image. Again, if I'd done it accurately, it would do. It should meet the image, which should be about there. But because I didn't measure it, you can see my image is somewhere over here. Mr. Gardener, you've got to be more precise than that. So get rid of that. And the image is actually over there. If I then do another ray, so we can do another ray going from, again, from the top of your object or the red dot over there. Do it maybe, say, going to there. And you can just repeat, whoops, that's a rubber. Repeat the process, dotting down, straight line down, hits the mirror, and then measure the angles, draw the normal, measure the angles, and then draw the ray reflecting off there. And don't forget, dot it back, and it should meet roughly where the image is. Oh, sorry, it's gone all the way up there. Hopefully that makes sense. If not, there's some good YouTube videos which are probably a bit clearer than that. I've made a bit of a mess here. Or look at your notes. I remember we did do this in your book and we drew it very similar to this back there. So you need to know how to do it and how to find what we call the image, which is where it appears to be. So if you look at a mirror, what you're seeing is an image of you and it appears to be the same distance behind and inside the mirror. You're obviously not there. You know you're not hiding in that mirror. But that's because the light appears to come from there. That's what these dotted lines here represent. The light appears to be coming from there, but actually it's bouncing off the mirror and into your eye down here. Obviously that eye's not actually there. I mean, it's just somewhere down here where you're looking at the object that was up here originally. I hope that makes sense. If not, again, drop me an email. I can point you in the direction of some useful resources. Thank you.